Well, thank you everyone for joining us for our December virtual star party. So I'm Dr. Billy Teets and I'm the acting director here at the Vanderbilt University Dyer Observatory. Joining us tonight, we have some of our regular presenters, which we love having every time. We've got Adam Thans from the Bays Mountain Park and Planetarium, Jeremy Veldman from the Memphis Astronomical Society, very festive Christmas tree behind him. And then last but certainly not least, Theo Wellington, right here in Middle Tennessee from the Barnard Seaford Astronomical Society. I also want to mention a few people we have working behind the scenes. We've got Helen Morissette, one of my colleagues here at Dyer Observatory, who's going to be helping us with questions tonight. And we've also got Brian Smokler of VU Communications, who's making sure that our stream is going out to you all tonight. So before we begin, I want to emphasize that as we're going through our presentations tonight, make sure that you post questions into the YouTube chat. We're going to try to get to as many of those questions as we can. If we don't get to your question in that particular segment, at the end of the program, which will end about 9 o'clock Central Time, we're going to go back through and try to get any other questions that we missed. So just hang tight if we don't get to yours right away. So tonight we've got a great program. Thankfully, we've been able to have some clear skies here in Middle Tennessee. Sorry to rub salt into the wound there, Adam, but unfortunately he's a little bit clouded out tonight. But we're going to be able to do a bit of viewing, and we're also going to be doing some discussions of different topics that you've heard in the news. We've also got some other segments dealing with telescopes. So let's jump right on into it. We're going to go over to Jeremy Veldman for our first presentation over in Western Tennessee, and he's going to be talking to us about an object that we often call M15. So Jeremy, take it away, please.
All right, thanks, Billy. First of all, quick sound check. Give me the thumbs up if you guys can hear me all right. Excellent. Well, first of all, I just want to say Merry Christmas, Happy Holidays, Happy Hanukkah, Feliz Navidad. Hope everybody's having a safe, happy, and healthy holiday season. Isn't December a great month? Winding down the year, we've got nothing but three weeks of partying as we wind down the year, and we're gonna do some astronomy partying for you tonight. So now in the unpredictable world of astronomy, you just never know. Last night, 100% cloud cover and rain. We got the same thing predicted for tomorrow night, but tonight here in Memphis, we've actually got clear skies, so it's a good night. Normally the clouds go out of their way to ruin an observing session for us, but fortunately tonight is not the case. So I'm going to go ahead and share my screen here for a minute. And hopefully everybody can see that all right. Give me the thumbs up. Excellent. So we're going to start with an object called M15, and this is Messier Object 15 in Charles Messier's catalog of 110 deep sky objects. This is a globular cluster, and now normally globular clusters are abundant in the summer skies, but there are a couple that are actually available in winter skies, and this is one of them, and it's a pretty interesting target, and it's also fairly easy to find, so I'll show you that in a second. But you can see that globulars are abundant in what's called the halo region of our galaxy, so they're not in the disk where our sun is right here, or the bulge, which is where some of the older stars are located, but the globulars are spherical configurations of stars in the galactic halo. They're very old. Some of them are as old as the galaxy itself, in fact, older. And they're just wonderful targets to get into the eyepiece of a telescope. Now, my weapon of choice for tonight is once again my 10-inch Dobsonian telescope. And this is a telescope I would recommend as a good beginner telescope. And for some of the reasons that we talked about in previous star parties, it's fairly portable. It's got a good size mirror, so you can do not only planetary, but also deep sky observing. And it's fairly cost effective. I mean, I bought this one used for just a few $100. So now tonight, this is kind of what happens when you connect a $4,000 eyepiece to a $400 telescope. So in this particular case, my buddy Brian, who's my new best friend, has a night vision eyepiece. And of course, we did this a few months ago, and we also did this recently, where we connected his night vision eyepiece to my Dobsonian. And night vision is really spectacular for enhancing features in deep sky objects. And for those of you who are wondering, this is the actual night vision eyepiece that he owns. And this is where you can get one if you have some discretionary income. And for those of you who are wondering if you're looking for any last minute gift ideas for me, well, here you go. And the nice thing about eyepieces is they're also excellent stocking stuffers because they're fairly, compact. So just a little tidbit of information there. So again, we connect it to a Dobsonian, hook it up to an iPhone, and then we see what we can see. And it's a great way to capture some deep sky objects. Now let's talk about M15 here. Again, it's Messier Object 15 in Charles Messier's catalog. Charles Messier in the 1700s, around the time of George Washington, was searching for comets and made a catalog of all the things that weren't comets and became world famous. So he's a spectacular failure who's now infamous. Now, what's interesting about this one, it's a globular cluster, and if you see them in the eyepiece of a telescope, after a while, they all kind of start to look the same. However, if you dig into this object a little further, it's pretty interesting. First of all, it's probably the oldest globular in our galaxy at about 13 billion years old. That's as old as the galaxy itself. It's also one of the brightest, about 360,000 times brighter than our sun. And what's also interesting is it's a very compact globular. It's undergoing a process of contraction. We're not exactly sure why, but it's hypothesized that possibly a black hole exists at the center of it, an intermediate sized black hole, or it could be undergoing core collapse due to so many stars in a compact area. In this particular case, there are hundreds of thousands of stars in this cluster, and more than half of them are in the inner 10 light year core of this cluster. It's 210 light years in diameter. So perhaps the mutual gravitation is causing this object to contract. The other thing that's interesting about this object is the first planetary nebula was discovered in a globular cluster, in this cluster, back in 1928, known as Piece 1. You have a large Dobsonian telescope. This would be an interesting object to try and find. And I'll actually point it out for you right here. You can actually see it. Now, a planetary nebula, of course, is what happens to a star like our sun when it gets toward the end of its lifetime and it exhausts all of its core hydrogen and then eventually helium fuel. And then the core and the envelope separate. And as the envelope expands away, it causes the gases to ionize and glow. And then that's where you get this beautiful planetary nebula. So it'd be pretty interesting if you have a large Dobsonian, either 20 inches or larger, to see if you could actually see this object within M15. And of course, it contains a number of variable stars and 9 known pulsars. So it's an interesting object. And of course, it's one of maybe 2 globulars that we know of. It's a little controversial yet whether this has a black hole at the center of it. But the thinking is that it probably does. Now, to find it, it's part of the constellation Pegasus, which is the great square in the winter skies. You look almost straight up toward the zenith, toward the western sky, you will actually see, and you can see this in the city as well. The great square is what we call it. And there's literally a trail of stars that forms one of the boots, or one of the feet, if you will, of Pegasus, the flying horse. And it literally gives you a trail of stars right to this object. So if you zoom in here to the lower right of the great square, you can see the star Markab. And then you literally just follow the trail through the Zeta and Theta, and then all the way to the Epsilon star. And that literally points the way to where this object is located. So it's fairly easy to find. It's a good target if you have a beginner scope and you've gotten past the moon and planets and you're looking to do some deep sky objects. This is very close to the zenith, again, toward the western sky. It's out right now. I'm actually looking at it. So that is M15. And here's what it looks like in the eye. Well, first of all, how do I find it? So technique that I use for a Dobsonian, because I don't have a go-to mount, is I use both a Telrad and a viewfinder. So I point my Telrad at the part of the sky where the object approximately is located. And of course, the Telrad has a plastic clear screen that forms a 3-ring target. It doesn't magnify the object, but I can point it directly at the part of the sky where the object is located. And then I actually use my viewfinder, which does magnify that part of the sky a little bit. and I look for something that's not quite a star. It's fuzzy, and that clues me in that that's likely a globular. So that's how I find globular clusters, star clusters, and then also galaxies, is in my right angle viewfinder, which are scrutinized at the Memphis Astronomical Society, but I get a lot of use out of them because I can combine it with the TELRAD for finding deep sky objects. My buddy Rick is laughing at me. So anyway, I use both, and that's how I can zoom in on globulars. And here's what it looks like. And you can see it's really a beautiful target in the eyepiece of a telescope. Very compact. This is one of the finest and most compact globulars. And you can see it's not a star. In an intermediate Dobsonian telescope, like a 10-inch, you can actually start to see the details of the stars popping out. This is a great target in my 20-inch. So, but you don't need a 20-inch to see detail. I mean, an 8 or a 10-inch Dobsonian, just zooming in here a little bit. And of course, with a Dobsonian, you don't have a tracking mount, so you got to move it by hand. But that's it. That's what a globular look like. I mean, they're great targets because it's like a firework just bursting in the eyepiece of a telescope. A lot of them out again in the summer skies, but there's a few of them out in the winter skies. And this is one of the finest one. You can see a really bright core, again, because most of the stars in this cluster are located toward the center. And it's a very compact object, but just very aesthetically pleasing, if you will. Just a very fine looking deep sky object. And globulars, just love them. They never disappoint. So M15, we call it the Great Pegasus Cluster. This is a classic target in the Messier catalog in the winter sky. And again, you're seeing it here through a night vision eyepiece in a 10-inch Dobsonian telescope. So that's it. I will go ahead and turn it back over to Billy, and let me know if you have any questions.
Doesn't look like we have any questions quite yet, but as folks are digesting everything, they may come up with something pretty soon here. So we'll keep a lookout for those. All righty. Well, thank you very much, Jeremy. Yeah, and I've seen M15 a number of times, and seeing other globulars like M13 on a good, dark, clear night. I mean, it looks like a little glitter box. They're just absolutely beautiful. So. All right, well, now we're going to go over to Goodlettsville and visit with Theo Wellington, and she's actually going to be discussing something that doesn't matter how clear the sky is tonight, we're never going to be able to see this at night. So Theo, I'll turn it over to you.
All right. Yeah, I thought we'd be clouded out, so I thought we'd look at, something that we can't normally look at just because it's not in the nighttime sky, right? So hopefully everybody's looking at the sun. And it's the brightest star in our sky. It's just out in the daytime because it's that bright. So remember to never, ever, never, ever, never look at the sun with just your eyes. Hopefully we drilled that into you in the solar eclipse in 2017 because the sun can damage your eyes. But to learn more about the sun, we like to use some safe ways of viewing. So come on here, baby. All right. So this is a normal night use telescope with the solar filter on the front. It's just like solar glasses except for the telescope part. So as a rule, solar filters go on the first thing that sunlight hits. If it's your eyes, then you need it in front of your eyes. If it's in front of a telescope, or if you're using binoculars, in front of the binoculars. Never put a filter on the eyepiece end. Some of them used to come that way, and that's a good way to get that cracked and again damage your eyes. So we don't do that. All right. Hopefully this plays. This is actually a video here. This is what the sun looks like through this telescope. What might surprise you about this image? First, of course, it's not yellow. Now, if we actually block all the wavelengths equally to where we can look at it, the sun is actually white. But usually our filters give the sun a nice orange-yellow color. Now this camera is a black and white camera, so I could Photoshop it and make it yellow, but as it is, I left it white. What do we call that cute little dot on the right side there? Let's see if I can point to it because it is pretty obscure. Yeah, it's a spot on the sun, and we call those sunspots. The astronomy is not hard. All right, let's see if we can get this to change. Come on, baby doll. Here we go. There we go. So this is a little bit closer up here. And you can see the edge of the sun just waving away there. That is not the sun doing that. That's our atmosphere. As it gets hot during the day, the atmosphere roils, and that's what it does to our star images at night too. But here you can see it rippling the edge of the sun. And you can also see how that poor little sunspot tries to go in and out of focus. Now, right after I shot this video, what happened next was that an airplane actually flew across the scene. And what was cool about that is that I of course clicked back on, so there's the contrail, and you can watch it slowly moving off and dissipating. So that was kind of fun. It's sort of surprising how often things like that, birds and planes, actually fly right in front of the sun while you're looking at it. What we do like to do with those is you take a little video and it's 1,000 frames real fast, and then you can actually stack those to get a much sharper view. The software is kind of magical. It will take the very best frames, the ones that look the most in focus, combine those, and then you get a little bit better looking picture. Now this is a really, really, really boring sun. We're just now coming up from the sun's solar minimum. So right now it's a good day when you have a spot. Now that's a white light filter. For more fun, you can get a telescope like this. This telescope is made to only look at the sun. And it's kind of cool. It looks at just a sliver. Instead of looking at all the light all the way across the spectrum, it picks out just that red light there that hydrogen emits. Let's see if I can tootle the cursor over here, just right here. So that's all it's looking at. And as a consequence, it's actually a very lovely shade of red. Now, this was an exceptional day a couple years ago where we had huge prominences coming off the side, and that's what this kind of filtering lets you see. Normally, the sun is so bright, even through filters, that you don't see those things on the edge. So that's kind of fun, that you can actually see prominences that are much larger than the planet Earth. Now, here's a picture, and the monitor is blowing this out a little bit. But this is actually 2 images because I can't expose it for both the prominences and the sun's surface. So 2 pictures mushed together, and sometimes you can have a little bit of fun that way as well. Now this is taken also with a black and white camera, but I used the color from that very first one with the big prominences was taken with my regular DSLR. So I actually used that color red to make this one red also, but that's about what you see with your eyes through that telescope. And let's see if we can get that to change. There we go. This is more typical what we see these days, a very, very, very blank sun. So it's been tough to get it, but it's fun to see that little bit of detail you can pick out with that, they call it an H-alpha telescope. They're fun because they make you look at the sun and watch it over time. It's really fun to watch it change even over a couple of hours, but then it's not useful at night. It only can look at the sun. So you kind of got to enjoy looking at the sun to have one of those. All right. Oh, what I wanted you to notice on that one, hang on. Let's see if we can see it on this one. These were actually 2 videos. You go back here to this one. Hopefully that's playing. There was something that whooshed right across the surface of the sun right when it started. And then I had another video where I slowed it down. Let's see if we can see this one. There we go. That little dot there that's cruising across the sun, that's the ISS. It's a little bit of fun sometimes to actually see that. And there used to be a site that kept track of that sort of thing and would send me an email when that was going to happen at my location. Sadly, that's guy retired from doing that, but so I'll have to find other ways of finding out when that happens. But it's really cool, and it's very location specific. So you have to know when it's going to happen for where you're at. So the sun has a really regular cycle of having lots of spots and not so many spots over about 11 years. And sometimes we have really active cycles, sometimes not. So the last sunspot cycle way over here was kind of a wimpy cycle. So we're just now starting into the next solar cycle, and so people are placing their bets as to how active it will be. It's about like weather forecasting 2 or 3 weeks out. So people will make their bets and they have reasons for them. They're just likely to be wrong. So this is the start of the next cycle here. We kind of had a little bit uptick this month. And so that made some people nervous, and they actually upped their estimate of how active it would be. But this is just this last cycle, and here we go, starting on the uphill side for the next cycle. And it's just magnetic fields. Now, our spacecraft have a really unique view, and this is just a super cool view from the Solar Dynamic Observatory. If you get a chance, go to SDO and check this out. This is the last 48 hours. The sun is fantastically dynamic. It doesn't look anything like the yellow smiley face that we draw. And it's probably a good thing we can't see this, because it would be scary if we could. You might have heard earlier this week they were thinking we could see auroras. That's because we had a big flare shoot out a CME, a coronal mass ejection our way, whole pile of charged particles. Sometimes when they hit our magnetic field, they interact and push the auroras down to our latitude. That actually didn't happen. That was a bust, but that's okay. And of course, the coolest thing about the sun and the moon together is that they do this. Hopefully, everybody here was there for 2017 to watch this. If you weren't, we'll get you another chance here. This is something that really should be on your bucket list, to see a total solar eclipse. There just are not words, and pictures do not do it justice. It's like the Grand Canyon. I had seen pictures all my life of the Grand Canyon, but until you go there and stand at the rim and your jaw's on the ground just like everybody else's, and everybody's saying, wow, it's so big. And it really is. Pictures can't do it justice. So same thing for a total solar eclipse. Until you're standing there with the shadow of the moon washing over you, it's just a whole different thing. So I hope everybody gets to do that. And I really hadn't planned on doing anything more than this one, and then hopefully the next one here in the States. But I had a chance last year to go to this wonderful location. This is La Silla Observatory in Chile, mountaintop observatory like they all are. And we had a group that went to do some science during the eclipse using some equipment that had been bought for 2017. We were taking pictures of the corona during the eclipse, but the camera could do that all by itself. So while it was doing that, we got to enjoy the total eclipse. So that was very, very cool and a whole lot of fun. And I'm glad I went last year, because this year it was a whole lot harder to get to South America. And this is actually the picture that we ended up with at the end of the eclipse. This is a very, they call it HDR, right? High dynamic range picture of what the corona was doing during the eclipse. So you can really see some fine structure and detail. And we actually had 2 stars show up in the image, which was also kind of fun. And then let's see. So Chile is reprising the eclipse this year. This will be Monday, and it will be live streamed, so you can watch it. NASA TV is going to do it in both English and Spanish. Time and date will have a stream. For us, let's see, that looks like 8:41 is when it starts Central Time. So get up in the morning and you can put this on. That'll be cool. For us, though, October the 14th, 2023, there will be an annular solar eclipse. That's when the moon is a little too far out. It can't quite cover the sun. So they often call these ring of fire eclipses. These, you have to wear your solar glasses the whole time. There's no taking them off. But that'll go over some pretty scenic areas in the southwest United States. So we're looking forward to hopefully getting out for that. And then just 6 months later, we get a total eclipse of the sun across not too far from us. Do not stay in Middle Tennessee, okay? This is not a test, and 90% is not an A. If you're that close already, go see the eclipse. You know, it's this is April the 8th. It's another Monday, so a long weekend. You know, we'll have to see what the weather's like. A lot of people are going to bet on Texas, because that time of year, Texas has better weather than, let's say, Buffalo. But you never know, so we'll have to see what happens. And you know, the sun is just so much fun, right? It gives us all of our heat and light. It gives us eclipses. And so here we are almost ready to celebrate the longest night, the solstice, which literally means the sun stands still, right? It stops its motion going south and having shorter and shorter and shorter days, and instead turns around and starts heading back north so we can look forward to longer days. So check out the daily picture of the sun. I got the website there at the bottom of that frame, and have safe solar viewing, everyone. So I'm going to turn that back over to Billy then. Stop the share. Here we go.
Thank you, Theo. That was really a nice presentation. We do have a couple of questions that popped up, and I've also got a couple of questions that I thought might be good for our viewers as well. Let's see. So the first question that was asked by our audience was, can you use those solar glasses that we use to watch the eclipse? Can we take those and look at the sun pretty much any time that we want to?
Yep. But before you use them, look through something like a bright light, like one of your halogen kitchen lights or something, and look for any pinholes in them. Hopefully you've taken good care of them and kept them in a nice place, but always check them first before you take them out and look at the sun. It has to be a really big sunspot to see it with just the solar glasses, but you know, if there is a big one, it's kind of a little bit of fun to be able to see that with your eyeballs.
When you were talking about the hydrogen alpha telescope, the H alpha, the one that only sees that one color of red, folks that are getting telescopes this year, they may see something like an H alpha filter for an eyepiece. Is that the same type of thing? And can you use that to look at the sun?
No, do not do that. So H alpha filters for night viewing are meant for looking at nebulas, really faint things that also do give off that same wavelength of light, but they are in no way meant to look at something as eye-burningly bright as the sun. And actually, I think they're also a much wider bandpass, but apart from that, yeah, don't look at the sun with those. Nope, nope, nope. It's the sun is just stupidly bright. And so the other filters are meant for doing photography at night.
Let's see. Oh, the video that you had of the International Space Station, the ISS, going across the sun, about how long did it take to go across the sun, would you guess?
I blink, second and a half, something like that, depending on how much of a cord. If it goes all the way across the middle, it might be 2 seconds. But honestly, you can, when I'm recording those, I start the recording before I think it's going to happen because I'm going to miss it. I mean, I'll have to watch it on the video later to see it.
The eclipse that is occurring this Monday, will we be able to see any part of that from Tennessee?
Nope, we're too far away even to see a tiny, tiny partial. So we'll just have to enjoy the view from, you know, people that are streaming it, and I'm sure there will be pictures all over the internet. So, and there are a ton of really frustrated eclipse chasers who are going to miss their first eclipse in, you know, however many that they've seen. But, you know, it's just really hard to travel right now. And I'm surprised they actually let anybody from the United States come down there at all the way we're at right now. But Chile is not too bad. And so people have gone down. They had to, you know, get tested and all that. But we don't get to see any of it, which is really sad. We will get to see, I think the whole US will be able to see at least a partial for the annular eclipse. So even if you can't travel for that, you're still going to be able to see something that day. So that's another good reason to keep those solar glasses around and keep them nice and safe. Although, trust me, people will be happy to sell you some new ones too.
Definitely. One final question about the 2024 eclipse, the total eclipse that's coming through the US. So you showed on the map how the path of totality, where you would see that beautiful corona, it's going right by Tennessee. So, you know, I think it actually just touches the upper northwestern tip of Tennessee. So if somebody was, say, 10 miles from that tip, and would they be able to say, I'm close enough, I'll be able to see it just fine? What are your thoughts on that?
It's amazing. You can get all the way down to 99% and it still looks like daytime. I mean, your eyes will adjust for one, but if you saw the total eclipse and you noticed how, like, it didn't really get dark until right at totality. So no, it's really not, if you're that close, just walk into it. But yeah, some bean field in that corner that sticks up into Kentucky there will hit totality. But and Carbondale gets their second eclipse in 7 years. But you know, Arkansas, If you have people you know there, I would just make a long weekend and call up your relatives that live somewhere in the path.
All righty. Thank you so much, Theo. All right, so now we're going to head over to East Tennessee to Adam Thans with the Bays Mountain Park and Planetarium. And unfortunately, he's clouded out tonight, but he's got a really cool topic that will be of great interest to everyone. It's a very useful tool. I use it all the time. So Adam, turn it over to you.
Thank you, Billy. Well, I hope everybody's been enjoying the views from our virtual program so far. We've had some great stuff covered with M15 and the sun and eclipses. And I am a professional astronomer, but I am a planetarium director. And so my goal in life is to share astronomy and to educate to others about astronomy. And to do that and to get prepared for a program, I use a program that's actually free that anybody can download, and it is called Stellarium. And just to mention, Billy's screen is highlighted, not mine. I'm not sure why. But anyway, I'm going to share my screen to show you Stellarium. Oops, okay. Okay, so you should be seeing the Stellarium program that I am using. First of all, it is a free program, and anybody can download it, and it is available for any platform, Mac, PC, Linux. There is also a web browser version, but it's very limited. I would just go ahead and download the version for your computer. And it's a great educational tool. So let's see. First of all, if you're wondering how to spell Stellarium, it's on the top of the screen. Stellarium. You can download the latest version. Once you open it, the first thing it's going to do is show you the sky at the current time, but not where you live, because it doesn't know where you are. It's going to show something like Denmark or something. You need to have it correctly placed. So notice on the side there in the left, you notice how that window popped out, and you have some tools. So this is the first thing that you want to do, is click on the location window, and you can type in where you are, and it will narrow down from an enormous list of places, and you can click on it. You can also just click on the map wherever you think you might be or want to be, and then use that. So it does show you your latitude and longitude and all of those things. But anyway, that's what you need to do first so that you are in the right place. Then you'll notice on the bottom, it tells you where you are. And there's also a whole bunch of other tools. And we're not going to go into all these details, but notice on the bottom, it tells you the field of view of your screen here. So we're seeing 77 degrees of the sky. Over here, it shows the date and the time. And so it should default to your computer time. So if it's daytime, let's say 3 in the afternoon, that's what it's going to show. I have it set for about 8:24, which is the current time, or close to the current time, which is what we see here. We're also facing south. So notice when I click on the screen, I'm clicked on it and I'm dragging the screen around. So it's pretty cool. It's showing you the whole sky and a bunch of stars, as you can see. So we're facing east. And let's see here. Let's face southeast at 8:24 this evening for tonight, December 12th. And you see these bright stars in the middle, and that should be recognizable as Orion. Well, you can learn how to turn on things. So here's constellation lines. Look at that. It's showing me the constellations. And so right here is Orion the Hunter with his shoulder stars, belt stars, and his two knees or legs. And so this hourglass shape is very recognizable. When you kind of mess around with the program, you'll learn hotkeys, which is basically keyboard strokes so that you don't have to click on buttons. So the letter C is for constellation lines. I press the letter C, it turns it off. Press it again, turns it on. Press it again, turns it off. Then if you want to show pictures of the constellations, notice that R, you see that R there? Constellation art, and then the R in the brackets. The letter R is your hotkey, or you can press the button. And we have some nice pretty pictures of the constellations. I have modified the art set. There is a color art set version. The version that it comes with, the program comes with, is kind of a grayscale, but it's still the same art. But you can see Orion right there. You can see below Orion, notice how the belt stars point downwards to the brightest star in the night sky called Sirius. And the spelling of it, Sirius, and it's part of Canis Major, the great dog. Let's turn on those constellation lines. Do you remember the letter? I don't know if I hear it out there. I'll just do it. I'll say it. The letter C. There we go. So here's our letter C. We're turning on the constellation line so you can see both. So there you can see how we see the constellation and also the mythical art. So let me turn off those lines. And again, let's drag the screen around. Oh, look what's rising in the east. We have these two people who look similar. I wonder, can you figure what constellation might that be? So I'm doing my education thing here. I'm not telling you the answer just yet. Two people who look the same. They're called the twins. And if you know the constellation name, maybe? Gemini, that's right. Now, Gemini the Twins is a famous constellation. And here's a little background lore for you. So you've probably heard the term of bigeminy or bigeminy. That is actually based on bigemini. And it was a saying that sailors would say to each other as kind of a form of good luck, because the twins were the kind of protectors and represented not the seas, but ocean faring, sailors. It's the ancient Greek version of a patron saint. And so Gemini was important to sailors. So they would say by Gemini, but it now has become by Jiminy. And that's where the phrase comes from. Look right below it. There's a crab. Can you guess that constellation? That's right, Cancer the crab. Then just below, rising in the east-northeast, look at that. I bet you can tell what that is. That's a lion. And his name? Leo. That's right, Leo the lion. And so there are things that you can turn on and off. I'm hoping I'm going to press the right button. Oh, wrong button, I'm sorry. So I wanted to turn on the ecliptic for you. And I think that's over in the configuration window. So let's do that. And let's see, I don't think I'm actually at the right place. No, I'm not. This is the wrong place, my mistake. But as you can see, there's all sorts of tools. I bet it's here. Let's see, markings. That's the grid. Oh, ecliptic update. All right, so I'm going to put that off to the side. So you see how there's some windows you can learn and play with. The ecliptic is the apparent path the sun makes across the sky. And it's also where we find the zodiac. The 12, actually 13 constellations that run along the ecliptic. No, sorry. The constellations, the planets do not have an effect upon our lives, but ancient astronomy is based on astrology. And so we do have at least that connection that's where things started from as far as getting the field going. But it was realized over time that no, the planets don't have any effect on us. But this is where you're also going to see planets. Maybe not exactly on that line, but close to it, because the plane of our solar system is generally along the ecliptic. It's within 5 degrees above or below. So you'll never ever see a planet in Ursa Major over here, but you will see it somewhere near the ecliptic. So let's drag that around. Oh, look at that. Can you see what's right here? Mars. Let me click on Mars, and I'm going to press my space bar. Notice what happened. It centered. And then I'm going to zoom in on Mars. So first of all, notice how you can see it near the ecliptic, and it's also near where we would see the zodiac. But here's something cool that we can actually zoom in on a planet and show even the moons of it. And this map of Mars is accurate. It actually is showing you, if you were able to have a super telescope to show Mars, that would be accurate as to what features you would see. You're not going to see Phobos and Deimos. I'll just tell you that right now. I'm zooming back out. Okay. Oh, I went too far. Now notice, look at this, our whole sky view. You're going to see this later with another image I'm going to show you. The ecliptic stretching across the sky. You're also going to see that it runs through these constellations. So that's Taurus the bull. Whoops, I'm sorry. Went through Gemini, Cancer, Leo, going the other way, Taurus. We see Aries the ram. We see Pisces. We see Aquarius. Those should be familiar constellations. We also see some other cool stuff. We see Eridanus, the river, right here down at the bottom, and Cetus, the sea monster, and the green, which is actually a whale. So lots of cool stuff to show. Let me turn off. Oops, sorry. Let me bring this up. Turn off the ecliptic. There's always things to learn. There's lots and lots of stuff to show. But let me go forward in time. Oh. Notice what's happening, because I know I'm near the end of my time here. Notice what's happening. I'm going forward in time. Notice how we see constellations rising in the east, setting in the west. And let me even do this so you can see that. So we're going forward in time. Notice the time clock down there. 5 in the morning, 6 in the morning, 7, and then we see sunrise. Everything is accurate. The moon's position, the planets, everything. And of course, you're not going to see the art in the sky, but it's very cool. Now, I don't think with my internet speed that you're going to see this well, but if you went much faster, what you would see is that you would notice how low the sun was in the southern horizon. That's because we're in winter, and our Earth, the northern hemisphere of the Earth, is facing away from the sun. And so we only see the sun get only a little bit above the horizon in the south, which is then why we have colder weather. It has nothing to do with distance. As an educational tool, you could kind of go super fast on this, and you would actually see the arc of the sun change. And then by the time you got to the summertime, the sun would be rising over here to the northeast, east-northeast, and going across like that to the north-northwest, the west-northwest. And so that would explain why we have a lot of sunlight in the sun in the summer, which is why it is so much warmer. So I'm going to stop that motion, and I'm going to stop my screen share. I know there is so much to show, but I want to see if you have any questions about Stellarium. Again, it is free and it's a great educational tool. One last thing I want to mention. What's really cool is then, you know how you can change the speed of daylight, of days time going by? Well, what you want to do is then have that map of the Earth. And while that's happening, change your latitude of where you are and notice how it changes. And then watch the sun. Put yourself on one of the poles, like the North Pole, and watch the sun's path across the sky and see how cool that can be. And I understand why those very northern or very southern places like Antarctica are called what they are. Notice how I haven't told you. And so I see one question, is that Stellarium correct? Stellarium. Are there any other questions?
It doesn't look like we have any at the moment, but what if I wanted to see, for example, what the moon was doing on the day that I was born? Can you do something like that?
Of course. We all know how much Stellarium has built into it. You can go forward and back to pretty much any date. I would say the accuracy starts to get a little crunchy, I'll say, when you go about 10,000 years. But if you go to your birthday, or if you go to, 1,000 years ago, or 2,000 years, or whatever, it'll be accurate. And yeah, all you got to do, there is a place that you can put in your date and time. So you can put in even the exact hour you were born and see the exact sky at that moment. But realize it's where you are on the Earth is going to change what you see. And so, yes, you can do those things. You can see the moon phases accurately. It will show you eclipses correctly. And just like Theo was saying, how, if you were right on that edge and at 99.9%, you can put yourself at 99.9% on the Earth, go to the date, and see the Earth, the sun and the moon, and you're going to see that it just skims by, but you will not see totality. You will not see the corona, but it does show all of that alignment correctly, which is pretty cool. I see a question about is there a program, is there a version for an iPad? Not Stellarium, unfortunately, but there are other astronomy programs. How can I find variable stars with the software? I don't know if you can look for that. You'd have to look for specific stars. Billy, do you know?
There are other, they're called scripts that can be installed. I'm not sure if there is a script for a variable star. Somebody may have written one. As these versions of Stellarium are constantly updated. In fact, you can get some of the very early versions if you wanted to. But you go to stellarium.org and you can find all these different ones. And one of the features now may be finding variable stars. It may mark some of the brighter variable stars. I honestly don't know. I have never seen that as of yet, but I may have one of the older versions, so right. I can't say for sure. But like you were saying, if you have a list of those stars, then you can do that search and Stellarium will point you directly to it.
Yes, it will. And it does have mathematical functions so that it can tell you like the exact separation of two objects in the sky, like which Theo will be talking about later, Jupiter and Saturn. And it can actually show you, and calculate the actual angular separation and do a lot of cool mathematical things too. So it's a really great educational tool for a lot of, right from early young ages, learning about seasons and moon phases a little later, solar system into your later elementaries. And it can even get into complex mathematics. So it'd be like high school level, college level material, all in that one program.
Yeah, I'll say that, for example, tonight, actually I'm up next, but the object that we're going to be looking at next, I used Stellarium to look up the coordinates for it and help me find it. So it's an incredibly powerful tool, and love that it's free and it's constantly being updated. So yeah, it's just a wonderful program. There's another question that just came in. Would a computer need to be running on an advanced operating system to be able to handle Stellarium? So especially, go back 15 years when this was first coming out. It didn't have as many bells and whistles, but you don't have to have a super, super fast computer to be able to run it. So, if you do find that maybe you have an older computer and the version, the brand new version that you download, Stellarium, is running kind of sluggish, or maybe your computer's having issues, you can always go back to one of the earlier versions that doesn't have so many functions on it, and it'll run it a little bit smoother. So,
yeah.
Let's see, we're running a little short on time. Just no fault of Adam or anybody else. We've had a lot of great questions. We had a couple of others that came in for Jeremy. Jeremy, you mentioned a good starter telescope earlier. Would you be able to mention that again?
Yeah, it's a 10-inch Dobsonian reflector telescope. And it's a reflector in that it uses mirrors, not lenses. So it gathers the light with a mirror in a big tube. And then the Dobsonian is the type of mount. It's basically an alt-as mount, meaning it swings up and down and then back and forth. It's a very simple design, very easy to manipulate, very easy to set up. In this particular case, it's a 10-inch, meaning the diameter of the primary mirror at the bottom of the tube is 10 inches in diameter. And then it's Orion. The brand is Orion. I bought it used for $350. A new one would be about $500-600. But always recommend anywhere from 6-8, or if you can get up to 10 inches in diameter, a Dobsonian reflector telescope.
And I'll just note that I've got a 10-inch. In fact, that was one of my first ones that I got when I started undergrad, and still have it, still love it. So yeah, it's a great telescope. I think there was one other. Jeremy, at the beginning, when you were talking about M15, and you were talking about how some globular clusters are so old, they may be as old or possibly even older than the galaxy itself. We had a question about how can something be older than the galaxy?
Yeah, it's a little bit of a mystery. I think most globulars, from what I've researched, and somebody can help me out with this, they form from the same clump of material. And then, of course, they're older stars, they've evolved off of main sequence. But there's some new research coming out now about galactic cannibalism, that perhaps our Milky Way may have swallowed galaxies in the past, and then maybe these globular clusters are actually the remnants of that galaxies that were stripped apart gravitationally. Older than the galaxy, probably not. As old as our galaxy, it's possible. There's a long history, in our galaxy of not only star formation locally, but close encounters with other galactic systems. And Bill, you probably have some insight into this as well.
Well, one thing I was just going to mention is that when astronomers get ages for things like the galaxy or maybe the M15 globular cluster, they can't say that it's 11.732 billion years old. They're going to say, based on the stars and the data that we've got, it looks like it's maybe, say, 11.5 billion years plus or minus 1.5 billion years. So what it's saying is that based on the data, that the age, based on everything that we have, it looks like it should be 11.5, but we can't rule out that it could be a little bit higher than that or a little bit lower than that. And so the galaxy is thought to be a little over 12 billion years old. The universe is 13.7 billion years old. So we might have a globular cluster that has a possible age range that may be a little bit above the age range of the galaxy. But one thing somebody else had pointed out, they were saying that maybe somebody was thinking about universe. So a globular can't be older than the universe because it's contained within the universe. So yeah, I think a lot of it just deals with the fact that there are uncertainties in pretty much everything related to astronomy. All righty, well, thank you guys for answering all of those questions. So we'll turn it over to me for just a few minutes here. We've got clear skies here in Brentwood at the Dyer Observatory. It's a little windy outside. But we're going to try to view an object. So to do that, we're going to use the Seaford Telescope behind me. It's a 24-inch Cassegrain reflector. So it also uses mirrors to form the image. It's set up a little bit different than a Dobsonian, but it's kind of like they're cousins of one another. So we're using that to observe something that is very appropriately named for this time of year, and that's the blue Snowball Nebula. So to get a good view of this, I'm going to have to turn off the lights, so give me 1 second. All right, so I've got my little ring light. We're going to have a little bit of a glow on me, but it shouldn't affect the telescope. So now let me share my screen. All righty. So Adam, if you can give me a thumbs up if you can see the snowball. All right, thank you. So I'm going to go ahead and start some other exposures here, but this was a 30-second exposure that I did a little while ago just to make sure that I had something in case clouds suddenly appeared over me, which is not uncommon here at the observatory. It's like the clouds know when we're trying to observe something. But what you'll see in this view are 3 stars here, and then we've got this fuzzy object here. Now, as this new image is just coming in, you might see that the telescope has moved just slightly because I'm not using a computer to help track this object. The telescope is basically moving at the preset rate and is trying to keep perfectly aligned with this object. But because the computer is not, making little corrections every now and then, you'll see that as new images come in every 30 seconds, that there might be a little bit of a shift, which is fine. So it's not really the object moving, it's just the telescope not tracking it absolutely perfectly. You may notice that we're getting a little blurry right now, and that's because of that wind. As the atmosphere is moving over us and the light from these objects is trying to pass through that atmosphere and get into the telescope, the light bounces around, which is what causes the twinkling of stars. So every now and then we might get an image that's a little bit blurry. The next image may be a little bit clearer. Let's see what we got. About the same. But the target that we're looking at here is what we call the blue Snowball Nebula. So this is what we call a planetary nebula, which is kind of a bad name because it has absolutely nothing to do with planets, other than that some of these kind of look round and faint, kind of like some of the distant planets in our solar system. These are not part of our solar system. This one, in fact, is about 2,500 light years from us. So in other words, the light that we're seeing tonight left that nebula about 2,500 years ago. But you'll notice that it's got some structure to it, and I'll show you a Hubble Space Telescope view here in just a moment. But you can see that it does have some structure, and in a big telescope, like the Seaford Telescope behind me, you can actually see a little bit of that structure with your eye. Now, for a smaller telescope, let's say like an 8 or a 10-inch Dobsonian, you would definitely be able to see this object. It would look very bluish green to your eye. A lot of this, which by the way, this is roughly a true color image. A lot of this greenish color is actually due to oxygen atoms being excited by light that is emanating from the core of that star. So the core, which by the way, this is a dead star. This is a small star, been about the size of our sun. It did not explode. The star, when it was running out of fuel in its core and the core began to collapse down and heat up, that caused the outer layers to puff up. And the star became a red giant. And eventually, the outer layers were gently lofted off into space. And so all of this greenish stuff that you're seeing is actually gas that formed those outer layers. So that gas is continually expanding outwards. To give you an idea of how big this is, it's about a light year across. So astronomers can actually determine the age of one of these nebulae, or in other words, how long ago did it actually start forming from its parent star. They have an idea of the distance, or a good estimate of the distance. They can actually measure, based on the properties of the light coming from that nebula, how fast that nebula is expanding. And if they know the distance to the nebula and how big it appears, they can actually figure out how wide it truly is. Okay, so if I know that it's 2,500 light years from me and it appears that big on the sky, that distance of 2,500 light years, that means that the nebula has to be, say, 1 light year wide. And if I know that the gas in that nebula is moving at, say, 500 kilometers per second, we can then say, well, how long would it take gas moving at 500 kilometers per second to become 1 light year wide? And so do that little bit of a math problem, and you'll find out that these nebulae are on the order of a few thousand years old. So this gas will continue to expand out into space. And as it gets farther and farther from that little white dwarf core, which is its light source, the nebula will get fainter and fainter. So if we went into the future in about 20,000 years, which by the way, Stellarium won't show you this, but if we look back at this nebula, in all odds, we would not see it at all because that gas would have expanded too much for it to be lit up by that little white dwarf, okay? So this object is also known as NGC 7662, or you can just call it the blue snowball. But it is something that is very easily seen in even a modest backyard telescope. You'll definitely notice that it's not a pinpoint of light like one of the stars that you'll see in a telescope, but it's an extended object. Okay, let me do a quick screen share. I'm just going to show you 3 other slides here. In fact, it's really only 2 other slides. Give me 1 second to do my screen share here. New share, and there we go. All right. So now you should be able to see a slide showing Stellarium. So here is another view, very similar to what we saw when Adam was showing us Stellarium, although mine isn't nice and color-coded like his. So, but if I go back, here's the Great Square of Pegasus, which was mentioned earlier. And right over here is where Jeremy was showing us M15. So right off the nose of Pegasus, okay? So right up in here is M15. Now we go back down, go up here, right where that square is. That's where that nebula is located, okay? It's actually not too terribly far from a fairly bright star. So you could use that star as kind of a marker. And if you find that with your telescope, then you could say, all right, according to my star chart, I need to go down to the next brightest star, hang a left, and I should find that nebula. But especially with the Dobsonian telescope, it has a wide field of view. You have a good chance of finding it. So again, this is one of these planetary nebula. A couple of months ago, Theo showed us the Cat's Eye Nebula, very similar object. But here is a really nice view from the Hubble Space Telescope. So this is a much sharper, closer up view. Now I say closer up, I don't mean that the Hubble was much closer to this nebula. It might have been 300 miles closer to it than I was when it took this picture. But remember, this nebula is 2,500 light years, and every light year is about 6 trillion miles. So the Hubble being in space does not make it really any closer to any of these objects. In fact, it might have been farther away, maybe on the other side of the Earth. So it was a little bit farther from this nebula than I was when it took this picture. But the reason it gets these really beautiful images is because it's above that blurring atmosphere that we were just looking through. Now, here is that little white dwarf. That core of that dead star, and again, this is all the outer layers of that star that were ejected. This core is collapsed down, has maybe about half the mass of the star, but it is now collapsed down so much it's about the size of the Earth. So this is a planet-sized object that has about half as much mass as the sun. Or in other words, imagine taking about 150,000 Earths and smushing them all into a ball and smushing them so much that that ball was still the size of the Earth. That new smushed Earth would be extremely dense. If you stick in a teaspoon into one of these white dwarfs and bring that teaspoon of white dwarf back to the Earth, it would weigh about 5 tons here on our planet due to our gravity. So it's extremely dense material, and it's mostly carbon. Okay. Now, one thing you'll notice about this image is that we've got much more of a blue color here. We've got some of this orange coming off. So why is it that my view is different from this? Well, the Hubble Space Telescope's final images, when they're put together, they often are some incredibly beautiful images. And so the scientists, when they are getting these images and then and doing research on them, they can then take them and make some final pretty pictures with them. But the colors here typically represent different elements that are within this nebula. Every element, every molecule has its own set of colors that it will emit. And so if we want to see, for example, where the oxygen is in this nebula, then what we can do is put in front of the telescope's camera a filter that blocks out all colors of light except for that one color that, say, oxygen will emit. And so any light that gets through that filter and forms the image, we will know has to have come from oxygen. So in this view, for example, the blue may be oxygen, and this red may be sulfur. And we may have some green in there that might be representative of hydrogen, okay? So just like when Theo was talking about the hydrogen alpha telescope, her telescope, which was looking at that one red color was only produced by hydrogen, which is what is allowing us to see those beautiful prominences coming off of the sun. So this nebula is pretty neat. Again, about 2,500 light years away, located up in Pegasus. And it was discovered in 1784 by Sir William Herschel. And if time permits, at the end of our program, we'll wrap up with looking at another object that he famously discovered a couple of years prior to this discovery. So with that, I think then I am going to see if we have any questions here. It doesn't look like we have any at the moment, but people may still be coming up with some questions. So if something pops in your mind, then just pop it in the chat and we'll come back to it towards the end there. So let me turn my lights back on. All righty, so let's see. Next on our agenda, we're going to head back over to Jeremy Veldman over in West Tennessee, and he's going to talk to us a little bit about telescope eyepieces. So Jeremy, please take it away.
All right, thanks a lot, Billy. So we've introduced this segment into our programming where we're talking about telescopes and accessories, and it's really meant to be an ongoing discussion. We do these star parties about once a month. Well, we do them once a month. So tonight I'm going to kind of kick it off with eyepieces. We talked about telescopes last time, and this is a pretty comprehensive subject, but I want to more or less introduce some concepts to you to sort of consider as you're not only considering buying a telescope, but also choosing eyepieces and accessories. So I'm going to go ahead and share my screen here. And hopefully everybody can see that all right. So there's a saying in astronomy when it comes to your budget that the money goes into the glass. And that's true whether you're buying a telescope, and it's certainly true whether you're buying eyepieces. One of the reasons why refractor telescopes are not necessarily recommended as your best beginner scope is because they are costly. And refractors, of course, use lenses as the primary collecting area. A 4-inch refractor is going to cost as much or more than, let's say, a 10 or a 12-inch Dobsonian. So a Dobsonian reflector uses mirrors, and mirrors are pretty cheap as far as collecting the light. Now, collecting the light is one thing, doing something with it is another, and that's where your eyepieces come into play. And just like the money goes into the glass with the telescope, it also goes into the glass when it comes to the eyepieces. And you need to choose wisely because it can get expensive real quick. So we'll talk about that in a second. But I want to sort of clarify something about telescopes and really their purpose. And you hear a lot about magnification and power. I mean, department stores love to do this whenever they have telescopes on the shelf. 200x power, or 400x power, or 100x power, whatever. It's a complete misnomer and a complete misconception about really what that telescope or any telescope is meant to do. The power is not in the telescope, it's in the eyepiece as far as what you do for magnifying and the light, if you will. So here you can see a very simple formula for showing you what power is in a telescope. And it's the ratio of the focal length of the objective of your telescope to the focal length of your eyepiece. It's a very simple ratio. So as you can see, the denominator of this formula is the focal length of your eyepiece. And simple math is the smaller the denominator, the larger is going to be that ratio. So that is how you magnify something in a telescope, is literally having a smaller focal length eyepiece. The smaller the number, the higher the power. The bigger the number, the lower the power. Now, you would think that higher power is better. That's not necessarily the case. In fact, we recommend you get a good low power eyepiece when you're getting started. The reason is because lower power, wider field of view, it gives you a clearer image. When you go to higher power, you're not only magnifying the image, but you're also magnifying the distortion. So, but anyway, this is the formula to consider when you're talking about power in a telescope. So it's really your eyepieces that determine the power of your scope. And you can see a simple example. Let's say you have a 48-inch focal length of your telescope and you use a half-inch eyepiece. We're using inches in this case. Typically the units are in millimeters, but let's just say we're using inches here. So if you have a 48-inch focal length telescope and you use a half-inch eyepiece, you're magnifying it 96 times. So, and again, although magnification is theoretically limited, another rule of thumb to consider is the limiting factor for your telescope is about 50 times per inch of diameter, whether it's a lens or a mirror. So if you have a refractor that's 2.5 inches wide, that's your primary collecting area, then that's going to give you a maximum useful power of 113 times. And I will tell you that for most of my observing, 113x is kind of the range I operate in. So now there's another formula here if you want to get more complex, and that is the limiting magnitude of what you can see. And this has to do with the object that you're viewing in the night sky. So our eyes under dark skies can see up to magnitude 6. So to give you an idea, the sun is, the smaller the number, the brighter it is. So the sun is negative 26 magnitude. The faintest stars that we can see in the night sky are +6. So we can't get beyond +6 without a telescope. So, and if we go up to +7, +8, again, they're not naked eye visible. So the limiting magnitude of your telescope is going to be determined by this formula here, 9 + 5 times the log of the diameter in inches. So if you have a 4-inch telescope, you plug that number in and you can see up to 12, +12 magnitude. So that's about twice what our naked eye can discern. So that's the capability, the limiting magnitude of a 4-inch telescope. So, but let's not overcomplicate it. The real ratio to consider is this one right here. The focal length of your objective divided by the focal length of your eyepiece. And the lower the number on your eyepiece, the higher the power. So with that said, here are some eyepieces that I personally own. This is an Explore Scientific line. And the big one in the middle is the first eyepiece I ever bought. That is a 20-inch low power eyepiece. And again, the 20, well, yeah. So it's actually 20 millimeters. I'm sorry, it's not 20 inches. I think, yeah, it's 20 millimeters, not 20 inches. Got to get my units right here. Okay, millimeters. So this is a 20 millimeter eyepiece. So again, focal length of the telescope in millimeters divided by the focal length of the eyepiece. That gives me the power. And I bought this one brand new for about 300 bucks. You can get it used much cheaper than that. The other 4 eyepieces that you see here, I recently picked up used from our Facebook page. And the one on the far right, the 6.7 millimeter eyepiece, I probably will rarely, if ever, use because the power is just simply too high and it's not practical. So I will use the 20 millimeter quite a bit, and then maybe the 11 and the 18, and that's about it. So you don't need 15 or 20 eyepieces to enjoy this hobby. You really only need 2 or 3. I use on any given observing night, maybe 2 or 3 at the most. But Al Nagler is kind of the expert in this field, and he has manufactured a couple of different lines of premium eyepieces, the Nagler line and then also the Ethos. I own a few of them. They're really expensive. They're beautiful eyepieces, but they are cost prohibitive. If you were to get these counterparts in the Nagler line, you would be paying about twice what I paid for these. So the 20 millimeter, I use that one quite a bit, 300 bucks new. The rest of them I bought used, 450 for the 4. So you're looking at 750 bucks worth of eyepieces right here. I also loan these. And again, the big one in the middle, the 13 millimeter Ethos, I use this one a lot. I love this eyepiece. It's a premium eyepiece, brand new. It costs, I think, about $550, 600 bucks. But again, I have a 20-inch Dobsonian. I have a 10-inch Dobsonian. The eyepiece costs more than the telescope in the case of the 10-inch. But if you're going to buy a big mirror, you know, for me personally, I wanted to spend the money to get an eyepiece, a good eyepiece. So that 13 millimeter Ethos, it's kind of a medium power. I use it a lot. That's my go-to eyepiece. I love it. I've also used the 13 millimeter Nagler on some of my smaller scopes, like my 3.5-inch ETX. It's a good planetary eyepiece. I used it quite a bit for the Mars opposition a couple months ago. The one on the left, the 8 millimeter, I probably won't use. I almost never use that eyepiece. Now, I have used it for Uranus and Neptune, which are out this time of year, but that's about it. If I had to do it over again, I'd probably go to the 10, and that's it. The one on the right is a Meade 10-inch or 10 millimeter eyepiece. Also, it's not a Nagler or an Explorer Scientific. I picked this one up for about 100 bucks brand new, and it's been a good planetary eyepiece for me, relatively cost effective. So it's a good option to consider if you're looking for a good eyepiece choice for higher power planetary stuff that isn't going to be cost prohibitive. Look for the Meade line. But anyway, I want to mention one other concept. I know I'm throwing some stuff out here, but not only power, but another thing to consider when choosing an eyepiece is something called exit pupil. And that is the ratio of the eyepiece focal length to your telescope's focal ratio. In the case of the eyepiece focal length, it's written right on your eyepiece. In this case, I'm showing you a 32 millimeter Plössl. Plössls are good starting eyepieces. A lot of telescopes come with a Plössl as your low power. So this is a 32 millimeter Plössl. Again, 32 millimeters meaning it's low power, and it would be a good eyepiece to use as a beginner eyepiece, a Plössl line. So now your telescope focal ratio will typically be something that's marketed with your telescope. So the one I showed you earlier, the 10-inch Dobsonian, that is an f5 telescope. So the focal ratio is 5. So if you did the math here, if you, let's say you took my 20 millimeter eyepiece and you divided it by the focal ratio of my telescope, 20 divided by 5 is 4. So my exit pupil would be 4. That's how much light is actually reaching the pupil or the pupil of my eye and actually forming an image. And I'm going to skip over this because of the time. But here's what exit pupil essentially means. So, and another reason why, you may not, you may want to consider limiting your eyepieces to about 10 millimeters max, because a fully dilated pupil under dark sky conditions, you may get maybe 5 to 7 millimeters, depending on your age. Younger people, they can get 7 or higher. People like me, I'm getting a little older, 5 millimeters is probably the max. So how much light is actually getting into my eye, that's determined by exit pupil. So if I have too small of an exit pupil, let's say I use a really high power eyepiece and I'm only getting 2 millimeters or less than 2 millimeters of light, it's too dim. It's too little light that's actually getting into my eye to form a good image. So, which is why, for me personally, 10 millimeters is probably as high power as I want to go, unless I'm looking at really bright stuff like, bright planets. So we cover these concepts in this video on our YouTube channel, as well as some other choices to consider for eyepieces that are cost effective. You're seeing here a 9 millimeter Morpheus, 76-degree field of view, and then also an 18 millimeter ultra flat field. I don't own either one of these eyepieces. My buddy Brian does, loves both of them. Check this video out. It's on our YouTube channel. We get into, we discuss these concepts in more detail, as well as some other cost-effective eyepieces to consider. So that's it. Are there any questions?
Yes, we do have one question. Can you talk about eye relief, specifically for those of us whose vision isn't as good as it used to be?
Right. Yeah, the more eye relief, the better. And think of specific numbers. Rick, do you know specific numbers on eye relief, a good eye relief for somebody who's a little bit older in terms of millimeters? Most eyepieces have a little rubber cup. Yeah. No, eye relief. How much eye relief? Couple of millimeters, right? 7 or 8 millimeters. Okay, 7 or 8 millimeters would be good eye relief for. Oh yeah, exactly. If you wear glasses and you're observing, and a lot of people do. I have contacts in tonight, but a lot of times I'm using glasses when I observe. You need more eye relief. So again, with a premium eyepiece, like the ones we showed you, that is an advantage where you'll get 7 or 8 millimeters of eye relief. And they have a little rubber cup that bends over and you can open up. And again, you get that eye relief. It's all about contrast, right?
Will you remind us of the best binoculars for night sky viewing? Yeah,
a good set of binoculars would be a 10 by 50 Oberwerk, Oberwerk. It's a good set of handheld binoculars. I don't know what the cost is off the top of my head. But that's a good starter set of binoculars.
And two telescopes we haven't really talked much about, but are Maksutov Cassegrains better than Schmidt Cassegrains?
Oh, that I wouldn't know, to be honest with you. I would probably still recommend the Schmidts, but you tell me. I'm more a Dobsonian guy.
Yeah, I would say that the Schmidt Cassegrain would probably be the one that I'd go with as well, because that front meniscus lens. So for those, we haven't really talked about this much, may not have talked about these particular telescopes at all in this program or on previous programs, but there are many different styles of telescopes, and there are some called catadioptric, which is, it's not a reflector, it's not a refractor, it's a blend of the two. So Schmidt Cassegrains are kind of like the big telescope we have back here, except at the front there is a corrector plate, which originally was to help refocus light for the mirror so that you would get a very nice sharp image. And that's a topic for another discussion because we'd have to go into more detail. But the Maksutov Cassegrain doesn't just have this corrector plate, it's actually got a lens at the front. So I would say purely from the standpoint of money, that the Schmidt Cassegrain would probably be the one to go with, because the Maksutov, you've got to grind a mirror, you've got to grind lenses, and Schmidt-Cassegrains, you can actually get a very large diameter as well for a reasonable amount, whereas Maksudov might be 5 inches at most before you start getting into the few $1,000 range. But that's just my 2 cents, and some of you out there watching may say, no, I totally disagree with that, and that's fine. Just based on my experience, I think that's what I'd have to go with. Theo, do you, or Adam, do you all have any input on that?
I prefer Maksudov Cassegrains. It's just a personal thing.
That's
And
fine.
the reason being is it provides a much sharper and higher contrast image, especially when you get to planetary objects or even star images. That it's just the quality of the image is a lot tighter. You can get, as an example, the Meade ETX 90, the proper one, which is a Maksudov Cassegrain. It's a 90 millimeter scope. It's teeny, it's this big, it's tiny. I mean, that's how long it is. It'll fit in a backpack, but it will provide really amazing images. It's not a light gathering bucket, but it's an excellent scope. And if you ever see those images from that, much larger version that astrophysics makes, those are amazing images. But Questar also makes that type of telescope, and those are very expensive. But the Meade ETX 90 millimeter is like $350, $400 for the whole setup, tripod included, maybe $500 for all of it. Whereas the Questar version of the same scope is $3,500. So, and I have the Meade one, and it's an excellent telescope. It is very small. If you want an 8 or 10 inch Cassegrain type folded image, folded telescope where it's a short tube, then yeah, Schmidt-Cass is going to be much better for your much better bang for your buck, and they are excellent. They are very good, but depends on what you want.
Yeah, and I guess it would depend if you're going to be doing brighter planetary stuff that doesn't require as much light gathering power versus dimmer deep sky stuff, which is probably Schmidt would be a better fit for that.
And also consider nature. If people want to use it as a spotting scope or a spotting camera lens to add, like a lens to add to their camera, but with a lot of magnification behind it, I mean, you would get some, you really would get some stunning images of birds or whatever if it's nature studies. And so that is another avenue of use. But I'll stop talking here.
No, it's good. It's good discussion.
Theo, did you want to add anything?
It sounds like a good way to start an argument between, amateurs. Drop that in and say, which one do you like best? But it's kind of like what Adam made really good points about how, it kind of depends on what you're doing. And so if you do a lot of a particular thing, then different designs are going to maximize that. On the eyepieces, I've had people come up to us at star parties and go, how can you pay that much for an eyepiece? And I go, how much did you pay for your last set of these? And I can tell you there is just a whole lot more value in an eyepiece than there is. I mean, these things don't cost $30, honestly, to make it. They charge us ridiculous. But anyway.
Yep. My favorite eyepiece is the 31 millimeter Nagler. I don't own it, but I would have no problem especially if you have a 20-inch or even a 16-inch Dobsonian, spend the money on the eyepiece. It's a phenomenal eyepiece, 31 millimeter Nagler, but it is expensive.
It's like falling into space to look through one of those. It really is. They're amazing. And that's why both people in the family shouldn't have the same habit, because you spend money.
Yeah.
And you don't need to spend a lot on eyepieces at the beginning. I mean, Plossels are excellent eyepieces in general.
Yep.
And those are like, it depends, $50 to $100 each.
Yep.
Eyepieces last your lifetime. I don't know how many. I mean, some people collect eyepieces.
Yeah, and you don't need a lot of them. One or two. I would say a good low power and a good medium power.
Right. Yeah, you do not need a lot. You just need the right range of, low to high power, but it's not that super high. And that'll serve you for your life. Whatever telescopes you have, plural, you can use the eyepieces on any of them.
Yep. Exactly.
I know we've got another question in the queue, but let's hold on to that one so we can get to our next presentation. We'll come back to that about the space station. But we're going to go back over to Theo, and she's going to tell us about something that we've probably all been hearing a lot about in social media, probably even on the news lately.
All right, so I couldn't resist this. Let's see what this looks like here. Back in the day, conjunction junction, yeah. So we've been hearing a lot about this, depending on the thing, really rare or once in a bajillion years, and then there's numbers that get tossed around all over the place. Okay, so in rough terms, though, a conjunction is any time a couple of celestial objects get together kind of close to each other in the sky. This happens to be a very lovely conjunction of Jupiter, Venus, and the moon, and you can actually tell which one is which because that's the order of brightness right there. So these things happen because, like Adam said, the planets travel along the ecliptic. So as they move, they're going to eventually get close to one another. That's just sort of a natural thing. This is the canonical textbook version of what you see, and I hate it because it's so wrong, and that's why we get confused about these things. So this is just bad. So we're going to head out into space a little bit. This is kind of a top-down view of the solar system. So, and it shows where the planets are today, actually. So that's Pluto out here, Neptune's the blue guy, Uranus right there, and this is Saturn and Jupiter, okay? Everybody travels at their own speed in their orbit, and the further out you are, the slower you're going. So the inner planets, the further in you go, end up lapping the outer planets, however often they go around. So if we zoom in a little bit, here's the inner solar system. Here's Earth. We've just lapped Mars. That happened at when we were at opposition there. But if you look from Earth across the solar system, and actually I think I did put an arrow in there for that. There we go. That's what we're seeing in the sky right now. We're seeing Saturn and Jupiter really, really close to each other. Now, I didn't want to try this live, so I got a video up. And let's see if yeah, it's running. So this started in October, and I've centered Jupiter so that we can watch over time how Jupiter and Saturn get closer to each other. So there went October's moon. And we slowly, slowly approach. And I don't think it was real noticeable until recently. And now that they're really close, the difference night to night becomes really noticeable. And of course, as we're moving around the sun at the same time, they're moving lower and lower in the evening sky. So there went November's moon. And we keep going down. And I did this a really brute force way of simply taking a camera and making a video watching my screen. There's a better way to do it, but I didn't have time to fool with it. So, and then eventually on the 21st, they will be almost indistinguishable. They'll be really close, way less than the diameter of the moon apart. And then after that, they move back apart. Jupiter's going to start getting ahead of Saturn there in the orbits. And that's the last frame there is New Year's Eve. So that's what's happening in the sky. Now, these things come around. This is the closest conjunction since 1623. And when he was studying the conjunction of 1603, they come in about 20-year intervals. Johannes Kepler thought that the Star of Bethlehem could have been the occurrence of a great conjunction. Now, the fun thing was in 7 BC, there was what we call a triple conjunction of Jupiter and Saturn, where Jupiter and Saturn did this fun little dance. They got close, they moved apart, they got close again, they moved back apart, and then got close for one last time. And that has to do with the way we're orbiting at the same time they're moving. So that was kind of fun. These things happen from time to time. The next one will actually happen in 2239, so wait for it. So here's what it looked like on the 5th of December in the night sky. I've been trying to go out every so many nights and take a picture so that we can watch how it's actually changing over time. This was last night because I really didn't think I'd get tonight, and the clouds gave a little glowy thing going on there. That looks good. It's always fun when you don't have to Photoshop an effect. But then here was tonight. We actually did get tonight in. And so night by night, they're creeping a little closer. And at the end of this, it's going to be really fun because when they're at their closest on the 21st, on solstice night, you'll be able to see both planets in the same field of view in a telescope. And that's really, really cool. We'll have the moons of Jupiter and a couple of moons of Saturn also in the picture. So there will be a lot of fun picture taking going on that night. And I'm sure more than a few people vying for an astronomy picture of the day with that. So these things happen, like I said, it's like 19.86 years between them. So it varies a little bit time of year. But there's sort of a long list of what's happened from the 1800s forward. And, you know, some are really tight, some are not quite so tight because the planets' orbits aren't flat exactly. So when they meet, they might be in a place where their orbits tilt them a little further apart. But this time they're kind of hitting right where their orbits, from our point of view, almost intersect. So back in 1623, this would have been a really cool sight just before the conjunction. We would have had Saturn, Jupiter, Venus, and Mercury all in the evening sky. So this is what observers at the dawn of the age of telescopes, Galileo and Kepler, would have looked at this. It's one of the things I kind of like. I feel like these things connect us with observers across time. You know, we're seeing a lot of the same things that they saw. Now, at conjunction that year, it would have been a tough thing because it was really, really low and tight with the sun. And it would have been even more of a challenge because Galileo lives a little further north, and this I ran for me here at my latitude, and Italy's actually a little further north. Now, these things happen again, too. So in 2040, in about 20 years, we'll get to see another one. It won't be quite as tight, but again, right before the conjunction, this is even more amazing to me. Check out how many planets are in this sky. There's all of them. Mercury's going to be the hard one, but everybody's there within a span of 15 degrees. That's like putting your hand out on the sky and you'll be able to have all 5 naked eye planets right there. That's just super cool. And I mean, that's a little bit of an astronomy nerd thing, but I really enjoy seeing these kinds of arrangements. It's just the dance of the planets, but it's just fun that they do this in our sky. So put that on your calendar, 2040, end of August there. Now, as it happens, the actual conjunction will be in the morning sky. They'll go past the sun before they actually come back together for our point of view. So you have to get up in the wee hours of the morning. I sometimes do this, but not everyone does. So it's really nice when conjunctions happen in the evening sky instead. 2060, a little bit further apart again. April, that's not so bad. And then in 2080, there will be another extremely close conjunction, low in the dawn summer sky. Now, I'm not going to see that. And the heavens also remind us, watching these patterns, that our lives are short against the very long time scales of these motions. But hopefully my kids and grandkids will also take a moment to enjoy the view, knowing that I also looked up in 2020 and saw much the same thing. So hope for a clear night on solstice night. This is the view through a telescope here with Jupiter, a couple of moons, Saturn's large moon Titan. Iapetus would be a challenge, but you know, that's going to be really fun. But Billy's got the telescope to show it, so I hope we get a good night. This is almost something I would drive to see. If it's only, you know, a short drive to get to a clear sky, I might do that. Because again, it's kind of a once in a lifetime opportunity. So I hope people will get to see this. And again, it's just fun to watch. So go out every night now, not just on that night or hope for that night, but go out each night that it's clear at sunset. We all need a walk these days anyway to get out of the house and get some fresh air. So go out, enjoy the planets, watch them come together. And, there's also Mars. So there's a lot of fun things to watch. And of course, Orion coming up, like Adam pointed out, one of my very favorite constellations. I always check to make sure Betelgeuse is still there. So just a lot of good fun, and I hope people will go out again and enjoy the Dance of the Planets. And the program that was looking top down, by the way, is called the Worldwide Telescope. And it's not real super intuitive, but you can play with it. It gives you, Stellarium does the best job of, I'm looking from the ground up. That one you can use to look at the solar system from the top down. So you can get outside Earth a little bit and look back and see what the motions of the planets are doing. So anyway, I hope you guys enjoyed that, and let me send that back over to Billy.
All right, thank you, Theo. We do have a couple of questions, especially about binoculars. Will you be able to see much with binoculars, and is it worthwhile checking them out?
For as far as if you have a good pair of binoculars and you can hold your hand stupid steady, you can sometimes make out the moons of Jupiter. It's hard, especially with light pollution, but you can do it. It's right on the edge of what you can see. What I like about binoculars is that they bring into view some of the things that would be naked eye except for light pollution. So, for example, the Andromeda Galaxy, the Pleiades look spectacular in binoculars. And some of those globular clusters you can see with binoculars too. So they're really useful, especially if you're in the city and maybe you're in an apartment, you don't have a telescope, but you can use binoculars, go out and find some of the bright objects in the night sky.
Yeah, and I would just add that if you're having trouble actually seeing the two planets, and not just as one, then binoculars should separate it out for you. So you definitely see two objects really close together. And there was another question about if we'd be able to show the conjunction on the 21st. So here at Dyer, we're going to have a telescope set up, weather permitting, of course. If it's cloudy, we're not going to do this, but you can go to our website, the homepage, dyer.vanderbilt.edu, and we have a link on down the page about the Great Conjunction. And from 5 p.m. to 6 p.m. Central Time on December 21st, we are going to try to do a live stream of the conjunction through the telescope where you'd actually see both of them at the same time. One thing to keep in mind is that when we're starting to see them in the evening, they're going to be getting kind of low in the sky. So that means that we're going to be looking through more and more air as time goes on. And so the view might not be super spectacular. We looked at Jupiter and Saturn in the previous months, and we got some pretty decent views of those. But when those planets start getting low in the sky, all that air moving, looking through more and more air, it just really starts to muddle the view. But we're going to try our best to get some views there. So, so just check out our website. That's going to be a free stream, so it's just going to be like joining what we did tonight, except we're not going to have a set program. I'm planning on hanging around during the time that we're streaming to answer questions, kind of talk about what we're seeing, maybe talk about the planets, or just kind of random things like that. So, anybody else want to add anything about the conjunction?
I would say, given that it's getting lower in the sky and the weather being as unpredictable as it is, from now until the 21st, any opportunity you have to get out and view it, take advantage of it. I have a 3.5-inch ETX with a 31 millimeter eyepiece. I'm hoping to catch both of them now. Tomorrow night, it's going to be cloudy, but if we get clear weather early next week, even if it's not on the 21st, I'm going for it. So now is literally the time, any opportunity you have, because they're so close together, to try and get it.
Yeah, and I would say also, as we're getting, within a couple of days of the 21st, go out each night and you'll definitely see a change in how far apart they are.
And you need a clear view of the western sky, so no trees.
Oh, and you don't have to be out in the middle of nowhere to have super dark skies. Jupiter's going to be decently bright even from the city, but to see fainter Saturn, if you're in the middle of the city, you might have to have some binoculars. But yeah, just have a good, clear western horizon, and hopefully you'll be able to see it all right.
I have to walk down the street. It weirds out my neighbors, I'm sure, because I'm basically looking over their houses. But oh well.
Yeah. That's your story anyway, right?
That's my story. That's right.
Yeah, Jeremy is right. The whole thing is seeing that progression of the two getting together, and then as they separate, and you just never know with the weather. And you don't have to have a telescope. Binoculars are great, or just your eyes, just experience it.
All righty. Well, Adam, let's turn it back over to you to talk about one of my favorite wintertime objects.
Okay, thank you. Yeah, I mean, wow, this is a great meeting we're having here, a great program, lots of great topics and good discussion and questions. So I'm going to be talking about one of the celestial highlights of the night sky. I am hoping that our next viewing, I'm assuming in January, I'm hoping it'll be clear, and I hope I can do it then with the telescope, but we'll see. Maybe it'll be with yours with much larger scope, because you kind of need a light bucket for this. And that is the Great Orion Nebula. So what is it? Where is it? Let's start with where. And I'm going to do a screen share of that. In fact, okay. So, okay, you should be seeing, this is a screenshot image of Stellarium, and it's in the entire sky. So if you took the whole sky, the bowl of the sky above you, and flattened it as a map, this is what you would see. We're facing towards the south in this image. If we are facing towards the east-southeast, where my cursor is, and right above, you're going to find the constellation of Orion the Hunter, O-R-I-O-N, Orion the Hunter, and the very famous hourglass shape. Then we're going to modify that. I've added a little marker there. Right where the sword of Orion is M42, the Great Orion Nebula. Remember, Jeremy talked about Charles Messier, that comet hunter from the 18th century, and that he was looking for comets, and he made a list of things that were not comets. Turns out they're the 110 best objects to see in the night sky, of all sorts of different kinds of things. And M42 was the 42nd object on his list, and it turns out that it is a stellar nursery, a place in which new stars are forming. Okay, now I'm going to change my screen share to Stellarium again. And now I'm going to use a little bit of features. So I'm going to do, oops, wrong thing. So I'm going to do the search window. This is how you find objects in Stellarium. And okay, so M, notice what's happening. It's sorted out to M objects. I'm going to add the number 4. Oh, it's showing me M4 first, but I want M42. So I'm going to type in a 2. And you notice how it's highlighted there. I'm going to press enter. Well, I don't know why it's not. There we go. All right, see how it just zoomed in and centered? I'm going to press, remember the letter for constellation lines? Do you remember the letter? The letter C. And there is Orion. I'll briefly show you the picture. Remember the letter was R for the pictures, or art. Get it? Art, R. So we see Orion. Let's zoom in a little bit on Orion and his art right there. Let me take that. So we're looking in the sword of Orion. Here is the famous belt stars of Orion. And again, If you go downwards, they point to the brightest star in the night sky, Sirius. Getting a little star ID here. Let's go the other way with the belt stars. As we go up, we find the face of Taurus, the bull, the famous V shape. If we continue, we find the famous Pleiades star cluster. Let's go back to Orion. Okay, pressing the space bar centers whatever's highlighted. And notice that I am on the sword of Orion. We're going to zoom in a little more and a little more. And you can start seeing this nebulosity there. Okay, let me stop my share for a moment of that and then go back to a photograph that I took. Oops, right here. So this is a photograph I took with a 5.3-inch refracting telescope. I cannot remember the exposure, a couple minutes. And it is showing that famous kind of looks like a bird, an eagle of structure. If I was able to take a much longer exposure, which I do intend to do to get a better one, this is actually, for me, not the greatest photo, but it does work. Very faintly, you're not going to be able to see this, but I see very faintly some nebulosity, almost in a giant circle here. And this whole area is nebulosity. And notice how it's illuminated from these central stars. So I am going to zoom in a little bit on this picture. Let's go a little more. Okay. Now, you have the balance of overexposure to see faint objects and then low exposure to see bright objects. It's very hard to see, but there are 4 stars in the middle there called the trapezium, 4 very bright stars. These very bright stars are very hot, intense stars that are OB stars. They're just very giant, bright, very strong solar winds come from these stars. And they're doing 2 things. They are illuminating or exciting the gases that are that make up the nebula. So it's like having a spark plug in the middle of this nebula, and that spark plug is sending out these sparks and is electrifying and energizing the molecules and making them glow. It is making them fluoresce. So just like a fluorescent light bulb, there is electricity running through the gas that is in that long tube and making the gases inside fluoresce or excite them to a higher energy state so that they glow. And different chemicals, different gases will glow at different colors. Now, a fluorescent light tube is balanced with different gases so that you end up with white. But let's say you had just neon, you would get that famous neon red light that you see in neon signs. Hydrogen is going to be a different color. Oxygen's a different color, and so on. So we are seeing these different gases, and that's why you see these different colors. So the exciting energy is coming from the trapezium in the middle and exciting those gases. And in a telescope with your eye, even a modest telescope, you will see what looks like this huge cocoon of all these gases. What's also happening is that new stars are forming out of this gas. Eventually, the nebula will be gone, and we will see about 20,000 stars. And so it's just an amazing sight to see. This is visible to the unaided eye. You do not need any optics, but you do need a dark sky to see this with just your eyes. Even in a modestly light polluted environment, I'm not going to say the middle of a city, but let's say a neighborhood, a suburb area. And as long as you avoid street lights, you should be able to see with binoculars the Orion Nebula. And you should see it pretty easily. Not super bright, but you will see it. A modest telescope will show something like this, and you will get a start of a hint of color. I was lucky enough to see this in a 30-inch telescope. I saw purple. It was amazing in this thing. It was amazing. So I do not own a telescope that large at all. Our largest telescope is a 10-inch. Let's go. So here's kind of a, zoomed out. And so this star and here, this is the sword of Orion, this area right here. And so we are seeing all this great structure. Let's go back to Stellarium for a second. Here we go. Okay, so here's the Orion Nebula. Now in Stellarium, hey, it's pretty cool. I'm gonna zoom in. I'm gonna turn off the art. Sorry. Sorry, I'm like M42, enter, there we go. So now I want to zoom in on that and more. And so this has built-in photographs of deep sky objects. This is kind of a very compressed version of like a Hubble image or another type of image like that that is being used. So it does give you an idea of what's going on. And in the center is the trapezium with the 4 very bright stars. Let's zoom back out. Whoops. And my photograph was showing this area, this star, this, and this star here. These 3 that make up the sword. That is where the Orion Nebula is. And you may have noticed some nebulosity over here. That would probably be pretty cool for that night vision eyepiece that was used by Jeremy and his friend, because over here is the Horsehead Nebula, which is a dark nebula. It's gases that are in silhouette, and it happens to look like a horse's head. And right next to it is the Flame Nebula. So you can do a lot of cool stuff with Stellarium. So pulling out once again, I'm going to show you this. Let's see, right about here. Do you see this field of view? This is about a binocular field of view. So you're going to see pretty much almost all of Orion, and you're going to see the Orion Nebula as a decent sized chunk of your view, but it's not super zoomed in. This is a binocular view. This whole screen image, that is what you would see in binoculars. And I'm using 8x42s. So 8 power with 42mm lenses in the front. That's a common binocular you'd have around the house. It's not that expensive. So binoculars are really a great thing that you can use. And the darker the sky, the better the view. Don't look during full moon. Don't even bother. But okay, a little bit of information. It's about 1.75 kilo light years, or 1,750 light years away. And there's an NGC catalog number, the New General Catalog of 1976. It's very patriotic. But really, it's a diffuse nebula. It is a place where stars are being formed out of those gases. And it's just a lot of fun to see. And pulling out once again, find Orion. It is one of the easiest constellations. I'm going to turn off my lines. Remember the letter C to turn off the lines. And it's this hourglass shape right here. And notice that it's above the east-southeastern sky right now. I'm going to stop the share. And yeah, that actually kind of gets us almost back to time, I guess. If there's any questions, I'll be happy to answer, or any comments.
Doesn't look like there's any questions at the moment, but we may get some more in just a few. I did want to get back to a question that we didn't get to earlier, and that might hand this over to Theo, since she had mentioned the International Space Station. But one person had asked that she has seen the space station like 3 times this week from where she lives, and was wondering why it's happening so many times this week. Is that a common occurrence, or what?
Yeah, they tend to come in runs. So, it'll be for, a week or so, it'll be in the evening sky, and usually not at the same time every night, but you might have one really spectacular pass and then the next couple might be low in the sky. We had a particularly spectacular pass on a night that I didn't expect it to be clear, and so I forgot to mention it online. But I actually stepped outside, looked up, and said, "Oh, hey, look, there's the space station." But right now for us in Nashville, it's flipped over to the morning sky. So for the next 2 weeks, if you're out walking the dog really early, there'll be some opportunities to see it in the early morning sky. But it's just the way the station's orbit goes. If you've ever looked at one of those when they have mission control, and you have this line come up for one orbit and then it'll shift over and come back up. The space station goes around Earth every 90 minutes. And so for us, you'll have a couple nights and it'll shift over a little bit. So maybe one night we'd see it overhead, then the next night Adam might see it overhead, but we'd see it low on the horizon. So it's just as that orbit goes around, but we'll have a run in the evening of a couple passes for maybe a week or two, and then it'll shift over to the morning sky.
Okay. Let's see. Doesn't look like we have any other questions. I take that back. There was one person that had asked about the web address. I think it was for when we were talking about the live stream of the conjunction. So that was the Dyer website homepage, dyer.vanderbilt.edu. So if you went to our homepage tonight to get the link for this event, just go to that same page. I think it's the next link on down. Doesn't look like we have any other questions coming in. I'm just gonna switch over and just for about a minute or two, since we didn't quite get to the last object, but we had mentioned it. Let me do my screen share right quick. Oh, I did the wrong one. Hold on. All right, screen share, and there we are. All right, so not so much of a splendid view. I mean, I can't compare it to Adam's view of the Orion Nebula, but still, it's fun to show this guy. Looks diminutive on the screen, but this is the planet Uranus. So everybody's favorite planet to, pull out a joke on. So, but anyway, I just wanted to point it out, and I'll do one other screen share. Where did it go? There we go. So everybody else is using Stellarium tonight, so I'm going to use it as well. Looking south right now, Uranus is almost due south. In fact, it's right over here. So here's the constellation Pisces, Cetus down in here, and here's Taurus with the Pleiades right up there. So Uranus is right along that ecliptic line, just like Adam had mentioned before, but it's over, I believe it's technically in Pisces this year. I can't remember though. So not too terribly far from Mars. Do you need a huge telescope to be able to see it? Believe it or not, if you're not in the middle of a city anyway, and you've got a pair of binoculars and you know where to look, you can actually spot it with a pair of binoculars. You don't have to have huge ones either. It's actually just below naked eye visibility. Some people may have been able to see it if they're in very dark locations. It look like a very faint star. And you wouldn't really notice it that much because it's faint, and every year it doesn't move much through the sky. So Jupiter, for example, it goes completely around the sky about every 12 years. So it moves about 30 degrees through the sky every year. That's quite a lot. If you hold your fist out at arm's length, that's about 10 degrees. So that's a lot for Jupiter. But this little guy, Uranus being farther out, he takes 84 years to go around the sky. So he'll only move about 4.5 degrees every year. So it doesn't move much through the stars each year. And so that very subtle movement doesn't really catch your eye, especially since Uranus is so faint. But it is possible to see it. If you've got a modest sized telescope, maybe an 8 or 10-inch telescope, you'll be able to see that it's not a pinpoint, it actually is a little ball. And you'll be able to see that bluish green color, which is due to methane absorbing a lot of red or the redder colors of sunlight and reflecting those bluer and greener colors. So anyway, I just wanted to kind of end with that. Actually, let me switch my screen share one more time. So new share and then back here. All right, so again, here you can kind of see that little ball shape. We've got a little bit of turbulence in the atmosphere tonight, but I did want to at least point that out because everybody loves taking a look at Uranus. So with that, I'll let you take the jokes on, and we'll see if there are any other questions or if there are any other things that our presenters would like to add before we close out this evening.
My standard line in the planetarium was, "We know all the jokes, but it's beneath us to tell them."
Well, I'm going to take other questions.
This is actually a great target. It's a good challenge once you, like you said, whether you have a modest sized telescope. I love this one for my 20-inch in a dark sky. And when you get, when you get close to where it's located, you see a bunch of dots, a bunch of stars, and they all kind of look alike after a while. It's a good practice, or it's a good exercise to train your eye to recognize a planet, which looks more like a disk, than a star, which doesn't have as well-defined edges as you would with a planet. So Uranus is a great target for training yourself to look at planets, if that makes sense. It's always a thrill getting this one. Because, the other ones are naked eye visible, but Uranus is not.
There was a question if just a small set of binoculars would be enough to get the Andromeda galaxy.
Yes. It's a great binocular target.
Actually, I take that back. They said Andromeda Nebula, so I don't know if they meant Orion Nebula or Andromeda Galaxy, or if they were just referring to the Andromeda Galaxy like it used to be called.
Well, 100 years ago it was the Andromeda Nebula, right?
Yeah. But both of those objects, even with a small pair of telescopes, or binoculars, you should be able to pick out.
Yeah, M42 is a great binocular target.
Oh, there was one question: will the conjunction live stream be recorded for those that are out actually viewing it live that day? Yes, we are going to try to record that, and we'll have it on our website as well for viewing later on. I believe that is all of the questions for this evening. So if there's nothing else, I want to thank all of our presenters again: Adam Thans from the Bays Mountain Park Planetarium, Theo Wellington with the Barnard Seaford Astronomical Society, and Jeremy Veldman with the Memphis Astronomical Society. And also thanking Helen Morissette and Brian Smokler for all their help behind the scenes. And then, not to forget our audience, thank you so much for joining us this evening. It's always a pleasure for us to be able to do this because this is what we do all the time, and we miss not being able to do it in person. So this is the next best thing, and I'm so happy that, I should say, we are all so happy that you're able to join us on these. So look for on the Dyer website. We're more than likely going to be doing these right through January and February as well. So hope everybody has a great holiday season, and please stay safe out there. So, thank you all for joining us tonight.